Voyager 1, launched in 1977, is the most distant spacecraft ever sent from Earth. It moves away from us at a speed of about 38,000 miles per hour, roughly 11 miles per second. Despite traveling more than 15 billion miles from our planet, we can still communicate with it. To put this in perspective, if you could drive a car at highway speed toward Voyager 1, it would take you more than 19 million years to reach it. The distance is so vast that it challenges our ability to truly comprehend it. If you could stack dollar bills from Earth to Voyager's current position, the stack would extend farther than the distance light travels in an entire day. Light itself, moving at 186,000 miles per second, takes more than 22 hours to cross the gap between us and the spacecraft. If we think about this distance in human terms, it becomes even more staggering. Imagine walking toward Voyager at a steady pace of 3 miles per hour. It would take you more than 580 million years to reach it. That is longer than complex life has existed on Earth. The dinosaurs lived and went extinct in less time than it would take to walk to Voyager. The first multicellular organisms appeared about 600 million years ago. Voyager is so far away that it would take longer than the entire history of complex life to reach it on foot. Or consider this: if every step you took covered a mile instead of a few feet, it would still take you more than 15 billion steps to reach Voyager. If you took 1 step per second, it would require nearly 500 years of continuous walking. The human mind struggles to grasp such distances. We are creatures adapted to understand the scale of our immediate surroundings, not the vast emptiness of interstellar space. Our brains evolved to navigate forests and plains, to judge the distance to a tree or a river. The distances of space are fundamentally alien to our intuition. Another way to think about it: if the Earth were the size of a basketball, Voyager would be about 12,000 miles away. That is roughly the distance from New York to Tokyo and back again. And this basketball-sized Earth would be trying to communicate with a spacecraft the size of a grain of sand at that distance. The achievement becomes even more remarkable when viewed through this lens. So how is it possible to send commands across such incredible distances? How do we receive data from something so far away? And how much longer will we be able to stay in contact with Voyager 1? These questions touch on fundamental challenges of space exploration. They involve physics, engineering, and the limits of technology, but they also reveal something remarkable about human ingenuity and persistence. The Voyager missions represent one of the greatest achievements in the history of exploration, comparable to the first circumnavigation of Earth or the first flights by the Wright brothers. When Ferdinand Magellan set out to circumnavigate the globe in 1519, he faced enormous unknowns. He did not know if he would find a passage through the Americas, did not know how vast the Pacific Ocean truly was, did not know if he would survive. Only 18 of the original 237 crew members completed the journey, and Magellan himself was killed in the Philippines. Voyager faced similar unknowns, venturing into regions no spacecraft had ever visited, with no guarantee of success. The comparison is apt in another way. Just as Magellan's voyage expanded humanity's understanding of Earth, Voyager expanded our understanding of the solar system and our place within it. Before Magellan, people knew the Earth was round, but they did not know its true size or the extent of the oceans. After his voyage, the scale of the world was revealed. Similarly, before Voyager, we knew the outer planets existed, but we did not know their true nature. After Voyager, they became real places, worlds with their own stories. The story of the Voyager missions begins with a unique opportunity and with a vision that emerged from the early days of space exploration. In the 1,960 seconds and early 1,970 seconds, NASA had successfully sent missions to Mars and Venus. The Mariner spacecraft had flown past Mars in 1965, sending back the first close-up images of another planet. Those images revealed a cratered, desolate world, far different from the canals and civilizations that science fiction had imagined. The discovery was both disappointing and thrilling. Mars was not inhabited, but it was real, a place that could be visited and studied. The images showed ancient river valleys and massive volcanoes, suggesting that Mars had once been a very different world, with flowing water and perhaps a thicker atmosphere. Mariner 10 had visited Mercury and Venus in the mid-1970 seconds, revealing the hellish surface of Venus, where temperatures reach 800 degrees Fahrenheit, and the heavily cratered surface of Mercury, baked by the nearby Sun. Venus, shrouded in thick clouds, had long been imagined as a tropical paradise. The reality was far different. Soviet landers that reached the surface survived only minutes before being crushed and melted by the intense pressure and heat. The atmosphere is mostly carbon dioxide with clouds of sulfuric acid. It is a world that has experienced a runaway greenhouse effect, turning it into the hottest planet in the solar system, despite being farther from the Sun than Mercury. But the outer planets, the gas giants beyond the asteroid belt, remained mysterious and unreachable with the technology of the time. They were known only through telescopes, their surfaces hidden beneath thick atmospheres, their moons barely visible as points of light. Jupiter appeared as a striped globe with its famous red spot. Saturn showed its magnificent rings, but beyond that, little was known. What was Jupiter made of? Did the Great Red Spot ever change? Were Saturn's rings solid or composed of particles? These questions could only be answered by sending a spacecraft to see for themselves. Uranus and Neptune were distant blue-green dots, their features invisible even through the most powerful telescopes. Some astronomers were not even certain what color they were. Ground-based observations suggested they were blue-green, but the exact hue was uncertain. Were there clouds? Did they have rings like Saturn? No one knew. A young aerospace engineer named Gary Flandreau was studying planetary alignments when he realized something remarkable. He was working at NASA's Jet Propulsion Laboratory in Pasadena, California, running calculations on an early computer. The year was 1965, and Flandreau was part of a team exploring mission concepts to the outer planets. The computers of that era filled entire rooms and had less processing power than a modern calculator. They used punch cards for input and produced printouts on continuous paper. The work was tedious, running the same calculations over and over with slightly different parameters, looking for optimal trajectories. Flandreau was studying the problem of how to reach the outer planets efficiently. The direct approach, simply pointing a rocket at Neptune and firing, would require an enormous amount of fuel and would take decades. The outer planets would align in a way that happens only once every 175 years. This alignment would allow a spacecraft to visit multiple planets in a single mission, using each planet's gravity to boost speed and change direction. Flandreau realized that the alignment would occur in the late 1970 seconds, providing a narrow window of opportunity. He published his findings in a technical paper in 1965 that would change the course of space exploration. The paper, titled Fast Reconnaissance Missions to the Outer Solar System Utilizing Energy Derived from the Gravitational Field of Jupiter, laid out the concept that would eventually become Voyager. Without this technique, visiting all 4 outer planets would require 4 separate missions, each taking decades. A direct flight to Neptune would require so much fuel that the spacecraft would be impossibly large and heavy. The rocket technology of the 1970 seconds simply could not launch such a mission. Even reaching Jupiter required careful planning and a massive rocket. But with the gravity assist method, all 4 could be visited in just 12 years. The savings in time and fuel were enormous. The window for this opportunity was narrow, lasting only a few years in the late 1970 seconds. If NASA missed it, the chance would not come again until the middle of the 22nd century. The next generation to see such an alignment would be born more than 100 years in the future. Most of the people who worked on Voyager would not live to see the next opportunity. The concept was approved, and the mission was initially called the Grand Tour. The name evoked the tradition of young aristocrats touring Europe to complete their education. In the 18th and 19th centuries, wealthy young men would spend years traveling through France, Italy, Greece, and other countries, visiting museums, studying art and architecture, learning languages. The Grand Tour was considered essential to a proper education. Voyager would tour the outer solar system, visiting worlds no human had ever seen. Budget constraints later scaled back the ambitions. The original Grand Tour concept would have sent 4 spacecraft to visit all 4 outer planets and their moons. But funding was limited, and the mission was reduced to 2 spacecraft visiting Jupiter and Saturn, with possible extensions to Uranus and Neptune. But the core idea remained. 2 spacecraft would be built, capable of withstanding the journey to the outer solar system and beyond. They would need to function reliably for years, perhaps decades, far from Earth, with no possibility of repair or maintenance. Every component had to be redundant, every system robust. The design phase took several years. Engineers had to solve problems that had never been encountered before. How do you power a spacecraft when sunlight is too faint for solar panels? Solar panels work well near Earth, where sunlight is abundant, but at Jupiter's distance, the Sun appears 27 times smaller and dimmer. At Neptune, it is 900 times dimmer. Solar panels large enough to generate useful power would be impossibly large and heavy. The panels would need to be the size of several football fields, far too unwieldy to launch or maneuver. How do you communicate across billions of miles? Radio signals weaken with distance, and the signals from Voyager would be incredibly faint by the time they reached Earth. The challenge was like trying to hear a whisper from across an ocean. How do you protect delicate electronics from the intense radiation near Jupiter? Jupiter's magnetic field traps charged particles, creating radiation belts far more intense than Earth's Van Allen belts. A human near Jupiter would receive a lethal dose of radiation in minutes. The electronics would need special shielding, but too much shielding would make the spacecraft too heavy. How do you ensure the spacecraft can survive for years in the cold vacuum of space? Each challenge required innovative solutions, and the engineers rose to meet them. Some challenges were mundane but critical. How do you prevent metal parts from cold welding together in the vacuum of space? On Earth, a thin layer of oxygen prevents metal surfaces from bonding. In space, that layer is absent, and metal surfaces pressed together confuse. The phenomenon had been observed on earlier missions, where mechanisms seized up after long periods in space. Engineers had to carefully select materials and coatings to prevent this. Some surfaces were coated with special lubricants that would not evaporate in vacuum. Others were designed to avoid contact altogether. How do you lubricate moving parts when most lubricants evaporate in vacuum? Special dry lubricants and careful design were required. Some mechanisms used molybdenum disulfide, a solid lubricant that functions in vacuum. Others used special greases that could withstand the extreme conditions. Every detail mattered. There were also concerns about micrometeorites. space is not completely empty. Tiny particles of dust and rock float through interplanetary space. At the speeds Voyager would travel, even a grain of sand could punch a hole through the spacecraft. Engineers designed protective shields and placed critical components behind layers of insulation. The spacecraft would have to survive thousands of potential impacts over the course of its mission. Voyager 2 was actually launched first on August 20th, 1977. The launch took place from Cape Canaveral in Florida, carried by a Tangent Centaur rocket. The Titan was a powerful rocket originally designed as an intercontinental ballistic missile, later adapted for space launches. It stood over 160 feet tall and weighed about 700,000 pounds when fully fueled. The Centaur upper stage provided the final push needed to send Voyager on its way. The Centaur used liquid hydrogen and liquid oxygen, cryogenic fuels that had to be loaded shortly before launch. The launch window was precise, calculated to the minute. A delay of even a few hours could mean missing the optimal trajectory. The planets moved continuously, and the launch had to be timed to intercept Jupiter at exactly the right moment. The weather had to cooperate, the rocket had to function perfectly, and the spacecraft had to separate cleanly. Engineers watched nervously as the countdown proceeded. Any number of things could go wrong. A valve could stick, a sensor could fail, a component could malfunction. But the launch went smoothly, and Voyager 2 was on its way. The roar of the engines could be heard for miles, and the flame from the rocket lit up the pre-dawn sky. Voyager 1 followed about 2 weeks later, lifting off on September 5th, 1977. Despite launching second, it was placed on a faster, shorter trajectory, which is why it eventually overtook Voyager 2. The trajectory was more direct, cutting inside Voyager 2's path to reach Jupiter first. The naming might seem backwards, but it reflects the order in which they would reach Jupiter. Voyager 1 would arrive first, so it received the number 1 designation. The decision to launch Voyager 2 first was deliberate. If something went wrong with the first launch, there would be time to fix the problem before launching Voyager 1. It was a form of insurance, a way to maximize the chances of success. If a flaw in the design was revealed during the first launch, it could be corrected before the second launch. This conservative approach paid off. Both launches were successful, and both spacecraft functioned perfectly. The two spacecraft are nearly identical in design. Each weighs about 1,700 pounds and stands roughly as tall as a small car. The structure is built around a central bus, a 10-sided aluminum framework that houses the electronics and computers. The bus is about 6 feet across, providing a stable platform for the various instruments and systems. If you saw one in person, you would notice the distinctive golden color of its thermal blankets, designed to protect sensitive instruments from the extreme temperatures of space. The blankets are made of layers of aluminized mylar, a material that reflects heat and insulates against the cold. In space, one side of the spacecraft might be baking in direct sunlight, while the other side freezes in shadow. The temperature difference can be hundreds of degrees. The sunlit side might reach temperatures of several hundred degrees Fahrenheit, while the shadowed side drops to hundreds of degrees below zero. The thermal blankets help regulate this, keeping the interior at a stable temperature. Some components require precise temperature control to function properly. The computers, for instance, were designed to operate within a narrow temperature range. Their mission was to explore the outer planets beyond Jupiter, worlds that had never been visited by any spacecraft before. Everything about these planets was uncertain. No one knew exactly what the spacecraft would encounter. Would the radiation near Jupiter destroy the electronics? Engineers designed shielding and radiation-hardened components, but they could not test them under the actual conditions Voyager would face. The radiation environment could only be estimated based on observations from Earth. Would Saturn's rings contain large boulders that could damage the spacecraft? Ground-based observations suggested the rings were mostly ice particles, but no one knew for certain. If there were large rocks in the rings, a collision could destroy Voyager. The mission planners chose a trajectory that would pass above the ring plane, minimizing the risk. Would the moons have atmospheres that could interfere with observations? Titan was known to have an atmosphere, but its density and composition were uncertain. If the atmosphere was too thick, it might obscure the surface. These were all unknowns, risks that had to be accepted. Rocket engines alone could not provide enough speed to reach these distant worlds in a reasonable time, so mission planners took advantage of a rare planetary alignment. Without this technique, a journey to Neptune would take 30 years. With it, the trip could be completed in just 12. The difference was transformative, turning an impossible mission into a feasible one. This allowed the spacecraft to gain momentum by using the gravitational pull of multiple planets. This technique is called a gravity assist, or sometimes a gravitational slingshot. As a spacecraft approaches a planet, it falls into the planet's gravitational field, speeding up as it swings around. The spacecraft follows a curved path, like a ball rolling around the inside of a bowl. When it leaves, it carries some of that momentum with it, like a ball bouncing off a moving train. The analogy is imperfect, but useful. Imagine standing on a moving train platform as a train rushes past. If you could throw a ball at the train and have it bounce back, the ball would return to you much faster than you threw it. The train has transferred some of its momentum to the ball. Gravity assists work the same way, except the spacecraft is the ball and the planet is the train. The spacecraft approaches the planet from behind, catching up to it in its orbit around the Sun. As it swings around, it steals a bit of the planet's orbital momentum, speeding up in the process. The planet itself slows down by an infinitesimal amount, transferring a tiny fraction of its orbital energy to the spacecraft. Of course, with planets weighing trillions of pounds, this loss is completely negligible. Jupiter would need to perform billions of gravity assists before its orbit changed by even a fraction of an inch. The energy transfer obeys the laws of conservation of momentum and energy. Nothing is created or destroyed, just redistributed. The spacecraft gains energy, the planet loses energy, but the total remains constant. This is a fundamental principle of physics. Energy cannot be created from nothing. Voyager is not violating any laws of nature, it is simply redistributing energy that already exists. The mathematics of gravity assists are complex, involving precise calculations of approach angles, speeds, and trajectories. Engineers had to account for every variable, from the gravitational influence of the planet's moons to the tiny push of solar radiation. The slightest error could send the spacecraft off course, missing its target by millions of miles. Computer simulations ran for months, testing different trajectories, looking for the optimal path. Each simulation took hours to run on the computers of the 1,970 seconds. The trajectory had to balance multiple factors: the science return from each planet, the total mission duration, and the amount of fuel required for course corrections. Some trajectories would provide better views of certain moons, but would require more fuel. Others would be more fuel efficient, but would miss important targets. Finding the right balance required careful analysis and countless trade-offs. The final trajectory was a masterpiece of orbital mechanics, threading a needle billions of miles wide. Jupiter, Saturn, Uranus, and Neptune were all positioned in the same general direction as seen from Earth. This particular alignment will not happen again until the year 2150. It was a once-in-a-lifetime opportunity, and NASA seized it. The window was narrow. If the launch had been delayed by just a few months, the opportunity would have been lost for generations. The entire mission depended on launching within a specific time frame, when Earth and the outer planets were arranged just right. Mission planners worked backwards from the planetary positions, calculating exactly when the spacecraft had to leave Earth to intercept each planet at the right time. They had to account for the motion of Earth as it orbited the Sun, the motion of the planets as they orbited the Sun, and the speed of the spacecraft. It was a four-dimensional chess game, played across billions of miles and years of time. The complexity was staggering, requiring thousands of calculations and careful verification. Voyager 1 flew past Jupiter and Saturn, capturing stunning images along the way. The encounter with Jupiter happened in March of 1979. The spacecraft approached the giant planet at a distance of about 217,000 miles from its cloud tops. This might sound far, but in astronomical terms, it was incredibly close. For comparison, Earth's moon orbits about 240,000 miles away. The approach was carefully choreographed. The spacecraft had to pass close enough to get good images and make scientific measurements, but not so close that Jupiter's intense radiation would damage the electronics. The radiation environment near Jupiter is one of the harshest in the solar system. Electrons and protons trapped in Jupiter's magnetic field create radiation levels thousands of times higher than in interplanetary space. The spacecraft's trajectory took it through the radiation belts, and engineers held their breath, hoping the shielding would hold. It did. One image revealed the swirling atmosphere of Jupiter, showing bands of clouds and the famous Great Red Spot, a storm larger than Earth itself. The resolution of these images far exceeded anything possible from Earth. Details that had been mere smudges in telescopic observations became crisp, clear features. Individual cloud structures could be seen, eddies and swirls within the larger bands. The cloud bands showed intricate structure, with eddies and vortices at all scales. The atmosphere of Jupiter is in constant motion, driven by the planet's rapid rotation and internal heat. Jupiter rotates once every 10 hours, the fastest rotation of any planet in the solar system. This rapid rotation creates powerful winds that blow in alternating directions in adjacent bands. The Great Red Spot has been raging for at least 300 years, possibly much longer. Some astronomers in the 17th century may have observed it through early telescopes. Giovanni Cassini, the Italian astronomer who discovered several of Saturn's moons, may have seen the Great Red Spot in the 1,660 seconds. His drawings show an oval feature in the right location, though the identification is uncertain. The drawings are ambiguous, and it is possible he was observing a different feature. Robert Hooke, the English scientist who discovered cells, also reported observing a spot on Jupiter around the same time. Hooke's observations are more detailed, and many historians believe he was the first to observe the Great Red Spot. The storm rotates counterclockwise, completing one revolution every 6 days. Wind speeds at its edges reach 300 miles per hour. The storm's colour comes from complex organic molecules created by ultraviolet light from the Sun interacting with Jupiter's atmosphere. Scientists still do not fully understand why the storm has persisted for so long. Most storms on Earth last days or weeks, not centuries. The Great Red Spot appears to be fed by smaller storms that merge with it, providing a constant source of energy. Observations show smaller storms being absorbed into the Great Red Spot, like water swirling down a drain. It also confirmed that Jupiter has faint rings, something that had been suspected but never clearly seen before. The rings are made of tiny dust particles, likely knocked off Jupiter's inner moons by micrometeorite impacts. The moons themselves are small and irregularly shaped, remnants from the early solar system or captured asteroids. Their surfaces are heavily cratered, evidence of billions of years of bombardment. Unlike Saturn's bright icy rings, Jupiter's rings are dark and difficult to see except when backlit by the sun. They are made of small, dark particles that do not reflect much light. They were discovered only because Voyager was positioned just right to see them edge on. The discovery was almost accidental, a bonus finding that came from careful planning and a bit of luck. Engineers had programmed Voyager to take images in that direction, hoping to find rings, but not knowing if they existed. The images had to be heavily processed to bring out the faint glow of the rings. The discovery confirmed that ring systems are common among the giant planets, not unique to Saturn. The spacecraft discovered active volcanoes on Io, one of Jupiter's moons. This was the first time active volcanism had been found anywhere beyond Earth. The discovery came as a complete surprise. Engineer Linda Morabito was examining navigation images when she noticed a strange umbrella-shaped cloud extending from Io's limb. She was working late at night, processing images to help determine the spacecraft's exact position. The images were not intended for science, but for navigation, to measure the spacecraft's trajectory by tracking the positions of Jupiter's moons. Navigation images were typically low priority, processed after the scientific images. But Morabito noticed something unusual. At first, she thought it might be a processing error or a smudge on the image. She cleaned the image processing equipment and reprocessed the image. The cloud was still there. She called over other team members, and they realized what they were seeing. Further analysis confirmed it was a volcanic plume. The finding sent shockwaves through the scientific community. Before Voyager, many scientists believed Io would be a cold, dead world, covered in ancient craters like Earth's moon. The discovery of active volcanism was revolutionary. It changed our understanding of how moons could be geologically active. Plumes of sulfur compounds shoot hundreds of miles above Io's surface, painting the moon in shades of yellow, orange, and red. Some of these volcanic plumes reach heights of 200 miles or more, creating umbrella-shaped clouds of gas and particles. To put this in perspective, Mount Vesuvius, the volcano that destroyed Pompeii, had an eruption column that reached about 20 miles high. Io's volcanoes are 10 times more powerful. Mount St. Helens, the volcano in Washington state that erupted in 1980, sent ash 15 miles into the atmosphere. Io's eruptions dwarf even the most violent volcanic events on Earth. The plumes contain sulfur dioxide gas, which freezes in the cold vacuum of space, creating a thin atmosphere around Io. The atmosphere is constantly replenished by volcanic activity and constantly lost to space, creating a dynamic equilibrium. Io experiences constant volcanic activity because of tidal forces. Jupiter's immense gravity squeezes and stretches the moon as it orbits, generating internal heat through friction. This process, called tidal heating, makes Io the most volcanically active body in the solar system. The surface is constantly being renewed, burying old craters under fresh lava flows. Some estimates suggest the entire surface is resurfaced every million years or so. In geological terms, Io is incredibly young. While most moons in the solar system bear the scars of billions of years of impacts, Io's surface is smooth and crater-free, constantly renewed by volcanic activity. The mechanism behind tidal heating is elegant. Io orbits Jupiter in an elliptical path, meaning its distance from Jupiter varies. When Io is closer to Jupiter, the gravitational pull is stronger. When it is farther away, the pull is weaker. This variation causes Io to flex, like squeezing a rubber ball. The flexing generates heat through internal friction, melting the interior and driving volcanic activity. The elliptical orbit is maintained by gravitational resonances with Europa and Ganymede, two other moons of Jupiter. Their orbits are synchronized, creating a repeating pattern that prevents Io's orbit from becoming circular. Voyager also studied Europa, another moon of Jupiter. Beneath its icy surface, Europa is believed to harbor a vast ocean of liquid water, warmed by tidal forces from Jupiter's immense gravity. The surface is covered in cracks and ridges, suggesting that the ice is constantly being broken and reformed. The patterns resemble sea ice on Earth, with cracks filled in with new ice. The ice might be only a few miles thick in some places, with a global ocean beneath that could be 60 miles deep. The evidence for this ocean comes from several sources. The surface features suggest that the ice floats on a liquid layer. Magnetic field measurements suggest the presence of a conducting fluid, like salty water. Models of tidal heating suggest that Europa's interior should be warm enough for liquid water. This ocean might be one of the best places in the solar system to search for life beyond Earth. The water might contain dissolved minerals and organic compounds. Volcanic vents on the ocean floor could provide energy and nutrients, similar to the hydrothermal vents on Earth's ocean floor that support entire ecosystems in total darkness. On Earth, these vents support colonies of tube worms, clams, and bacteria that live without sunlight, deriving energy from chemical reactions. The bacteria oxidize hydrogen sulfide from the vents, creating a food source for other organisms. Could similar life exist in Europa's ocean? Future missions are planned to explore Europa further, perhaps even drilling through the ice to sample the ocean below. The challenge is enormous, but the potential discovery would be profound. Ganymede and Callisto, two other large moons of Jupiter, were also studied. Ganymede is the largest moon in the solar system, even bigger than the planet Mercury. It has a diameter of about 3,200 miles, compared to Mercury's 3,000 miles. It is the only moon known to have its own magnetic field, suggesting it might have a liquid iron core. The magnetic field is weak compared to Earth's, but its presence indicates that Ganymede has a differentiated interior with a metallic core, rocky mantle, and icy crust. Its surface shows a mix of dark, ancient terrain and bright, younger regions with grooves and ridges. The bright terrain appears to have been formed by tectonic activity, where the icy crust cracked and shifted, creating parallel ridges. Some ridges extend for thousands of miles, suggesting large-scale movements of the crust. Callisto's surface is ancient and heavily cratered, a record of billions of years of impacts. Some craters are so old they have been flattened by the slow flow of ice over geological time. Ice, under pressure and over long periods, behaves like a very viscous fluid, slowly deforming and erasing topography. Callisto appears to be a frozen relic from the early solar system, unchanged for billions of years. Its surface is a history book, recording impacts from the era when the solar system was still forming. Callisto might also have a subsurface ocean, though it would be buried much deeper than Europa's. Recent studies suggest that many of the outer solar system's moons might harbor subsurface oceans, making them potential habitats for life. The presence of liquid water, organic molecules, and energy sources creates the possibility of life in places we never expected. It then continued towards Saturn. The journey from Jupiter to Saturn took about a year and a half. During this time, the spacecraft continued to make observations of the solar wind and cosmic rays, gathering data about the space between the planets. This interplanetary cruise phase was scientifically valuable, providing insights into the environment beyond Earth's immediate neighborhood. The measurements showed how the solar wind varies with distance from the Sun, how it interacts with magnetic fields, and how cosmic rays penetrate the heliosphere. There, it observed Saturn's rings from close range and found shepherd moons that help shape and maintain those rings. These small moons orbit within the ring system, and their gravity creates gaps and keeps the rings from spreading out. The most famous gap is called the Cassini division, a 4,000-mile wide space between the main rings. The gap is not completely empty, but contains much less material than the surrounding rings. The rings themselves are composed of countless particles of ice and rock, ranging in size from tiny grains to house-sized boulders. Each particle orbits Saturn independently, forming a disk that extends hundreds of thousands of miles, but is, in most places, only tens of feet thick. The rings are remarkably thin relative to their extent, like a sheet of paper hundreds of feet across. The rings are a relatively recent feature, astronomically speaking. Scientists believe they formed within the last 100 million years, possibly from a moon that was torn apart by Saturn's gravity or shattered by a massive impact. The process would have been violent, grinding the moon into countless fragments. A moon that wandered too close to Saturn would have been pulled apart by tidal forces, the same forces that heat Io. The difference in gravitational pull between the near side and far side of the moon would overcome the moon's structural strength, ripping it into pieces. The rings will not last forever. They are slowly spiraling inward, raining down onto Saturn's atmosphere. Particles collide, losing energy, and gradually drift inward. In another 100 million years, they might be gone entirely. Future observers might look at Saturn and see a ringless planet, like Jupiter or Neptune. The rings are a temporary feature, a brief moment in Saturn's long history. We are fortunate to live in an era when they exist. It also discovered that Titan, Saturn's largest moon, has a thick atmosphere made mostly of nitrogen, about 90%. In fact, Titan's atmosphere is denser than Earth's. The surface pressure on Titan is about 1.5 times what we experience at sea level. Titan is the only moon in the solar system with a substantial atmosphere. Most moons are too small to retain an atmosphere. Their gravity is too weak, and gas molecules escape into space. But Titan is massive enough, about half the diameter of Earth, to hold onto an atmosphere. The atmosphere is so thick that Voyager's cameras could not see the surface. All they revealed was a hazy orange globe. The haze is made of complex organic molecules, created by sunlight breaking apart methane and nitrogen molecules in the upper atmosphere. These molecules recombine to form larger, more complex compounds, including some of the building blocks of life. The chemistry is similar to what might have occurred on early Earth, before life began. This discovery would later inspire an entire mission dedicated to exploring Titan more closely. That mission, called Cassini-Huygens, arrived at Saturn in 2004 and dropped a probe onto Titan's surface in 2005. The Huygens probe descended through Titan's atmosphere, taking photographs and measurements. The descent took about 2.5 hours, with the probe suspended beneath a parachute. It revealed a landscape of dunes, lakes, and rivers, not of water but of liquid methane and ethane. At Titan's temperatures, about -290 degrees Fahrenheit, methane and ethane are liquid. Water, on the other hand, is as hard as rock. Titan is the only place in the solar system besides Earth where liquid exists on the surface. The lakes near Titan's poles contain more liquid hydrocarbons than all of Earth's known oil and gas reserves combined. Some lakes are hundreds of miles across and hundreds of feet deep. The landscape is eerily Earth-like, with familiar features shaped by unfamiliar materials. Rain falls on Titan, not water rain, but methane rain. Rivers carve channels through the landscape. Lakes fill and evaporate with the seasons. It is a world where familiar processes occur, but at temperatures far below anything experienced on Earth. The methane cycle on Titan is analogous to the water cycle on Earth, with evaporation, cloud formation, precipitation, and runoff. Voyager 1 also found several new moons around Saturn, small, irregular bodies with cratered surfaces. Before Voyager, only about 10 moons of Saturn were known. Voyager discovered several more, bringing the total to about 18 at that time. Today, we know of more than 80 moons orbiting Saturn, though many are tiny, barely more than large boulders. Some are only a few miles across, too small to be spherical. They are irregular chunks of rock and ice, probably captured asteroids or fragments from larger bodies that broke apart. Each discovery added to the complexity of the Saturn system, revealing a dynamic environment with intricate gravitational interactions. It measured temperatures in Saturn's atmosphere and discovered strange features in the rings, including braided structures and dark radial patterns called spokes. Scientists are still working to understand how these features form. The braided rings are particularly puzzling, appearing to twist around each other in ways that seem to defy the laws of orbital mechanics. Each particle in the rings should orbit independently, following its own elliptical path. But the braided rings appear to be intertwined, as if the particles are somehow connected. The explanation involves shepherd moons and gravitational resonances, but the details are complex. The shepherd moons create waves in the rings, and these waves can interact in complex ways, creating the braided appearance. The spokes rotate with the rings and appear to be made of fine dust particles, possibly lifted by electrostatic forces. They come and go on timescales of hours, appearing and disappearing as the rings rotate. During Voyager's encounter, the spokes were prominent. Years later, when Cassini arrived at Saturn, the spokes had vanished. They reappeared later, suggesting they might be seasonal, related to Saturn's orientation relative to the Sun. The exact mechanism remains uncertain, but it likely involves the interaction of sunlight, Saturn's magnetic field, and tiny dust particles. After that, Voyager 1 continued its journey toward the outer edge of the solar system. Its trajectory carried it upward, out of the plane where most planets orbit. The path was deliberate, designed to maximize scientific return while sending the spacecraft toward interstellar space. The close encounter with Saturn provided the final gravity assist, accelerating Voyager to escape velocity. Escape velocity is the speed needed to break free from a gravitational field. At Earth's surface, escape velocity is about 7 miles per second. From the solar system as a whole, escape velocity depends on location, but at Saturn's distance, it is about 9 miles per second. As it left Saturn behind, it accelerated to its current speed, moving faster than any human-made object had ever traveled before. The spacecraft was now on a trajectory that would carry it out of the solar system entirely, never to return. The gravity of Saturn had flung it outward, giving it the final push it needed. Voyager 2 took a different path and flew by Uranus and Neptune, destinations that Voyager 1 never visited. The trajectory to Uranus took several years. The spacecraft traveled alone through the outer solar system, billions of miles from the nearest planet. During this time, it continued to monitor the space environment, gathering data that could not be obtained any other way. At Uranus, it discovered 10 new moons and found that the planet's magnetic field is tilted at an unusual angle. Unlike most planets, where the magnetic field roughly aligns with the rotation axis, Uranus has its magnetic field tilted nearly 60 degrees. The magnetic axis does not even pass through the planet's center. It is offset by about a third of the planet's radius. This strange configuration suggests something unusual about Uranus's interior. Perhaps the magnetic field is generated not in the core, but in a layer of conducting material closer to the surface. Or perhaps the field is in the process of reversing, as Earth's magnetic field does periodically. The planet itself is also tilted on its side, rotating with its poles facing the Sun. This means that each pole experiences 42 years of continuous sunlight, followed by 42 years of darkness. Imagine living on Uranus, where a single day lasts about 17 hours, but each season lasts 42 years. The poles would bake in sunlight for decades, then freeze in darkness for decades. The equator would experience a more moderate cycle, with the sun rising and setting every 17 hours, but its height in the sky would vary dramatically over the course of an 84-year orbit. The reason for this extreme tilt remains a mystery. Some scientists believe Uranus was struck by a massive object early in its history, knocking it onto its side. This impact would have been catastrophic, possibly stripping away much of the planet's original atmosphere. The collision might have been with an object the size of Earth or larger, a glancing blow that sent Uranus tumbling. The impact might also explain the unusual magnetic field if it disrupted the planet's interior structure. At Neptune, it photographed the fastest winds in the solar system, reaching speeds of over 1,000 miles per hour. The winds blow in the opposite direction of the planet's rotation, a phenomenon that still puzzles scientists. On most planets, the winds are driven by the planet's rotation and tend to blow in the same direction, but Neptune's winds are retrograde, blowing against the rotation. The mechanism is not understood. Neptune is so far from the Sun that it receives almost no solar energy, yet its atmosphere is incredibly dynamic. The source of this energy remains unclear. Some scientists think Neptune might have an internal heat source, left over from the planet's formation. When planets form, gravitational energy is converted to heat as material collapses together. Most planets have cooled over billions of years, but Neptune might still be warm inside, radiating more heat than it receives from the Sun. Measurements show that Neptune emits about 2.5 times more heat than it absorbs from the Sun, suggesting a significant internal heat source. It captured detailed photographs of both planets, revealing worlds of blue and green hues, unlike anything seen in the inner solar system. The blue colour comes from methane in the atmosphere, which absorbs red light and reflects blue. Neptune's blue is deeper and more vivid than Uranus, possibly due to an unknown atmospheric component. Some scientists speculate there might be an additional absorber in Neptune's atmosphere, something that enhances the blue colour. Others think the difference might be due to atmospheric haze. Uranus has a thicker haze layer that scatters light, making its colour appear paler. Neptune's atmosphere is clearer, allowing the deep blue colour to show through. The exact composition of the hazes is uncertain, but they likely contain hydrocarbons and other organic molecules. Voyager 2 also discovered geysers on Triton, Neptune's largest moon. These geysers spew nitrogen, gas, and dark particles into the thin atmosphere. The geysers are driven by seasonal heating from the distant Sun. Even though the Sun is incredibly faint at Neptune's distance, appearing as little more than a bright star, it is enough to warm nitrogen ice beneath Triton's surface. The ice evaporates, building up pressure until it erupts through cracks in the surface. The process is similar to how geysers work on Earth, but powered by solar heat rather than volcanic heat. On Earth, geysers like Old Faithful in Yellowstone are driven by underground magma in heating water. On Triton, the process is driven by sunlight warming frozen nitrogen. Triton is one of the coldest places in the solar system, with surface temperatures around -390 degrees Fahrenheit. This is only about 70 degrees above absolute zero, the coldest possible temperature. Despite the cold, internal heat drives the geysers, creating dark streaks across the moon's icy surface. These streaks can be hundreds of miles long, blown by Triton's thin atmosphere. The dark material is probably organic compounds created by radiation processing of methane ice on the surface. Charged particles from Neptune's magnetosphere strike the surface, breaking apart molecules and creating new compounds. Triton orbits Neptune in the opposite direction of the planet's rotation, suggesting it was captured from the Kuiper Belt, a region of icy bodies beyond Neptune. The capture process would have been violent, causing tidal heating that might have melted much of Triton's interior. Triton's surface is surprisingly young, with few craters. This suggests recent geological activity, possibly driven by tidal heating. Eventually, Triton will spiral inward and be torn apart by Neptune's gravity, creating a ring system that might rival Saturn's. The process will take millions of years, but it is inevitable. Triton is slowly losing orbital energy through tidal interactions with Neptune, causing it to spiral inward. When it reaches a certain distance, Neptune's gravity will overcome Triton's structural strength, tearing it into fragments. The resulting ring system might persist for millions of years before the particles slowly spiral into Neptune's atmosphere. After finishing their planetary missions, both spacecraft kept moving farther from Earth. Although Voyager 2 launched first, Voyager 1 is now farther away because it travels faster. Voyager 1 moves at about 10.5 miles per second, while Voyager 2 travels at about 9 7/10 miles per second. That speed difference might not seem like much, less than 1 mile per second, but imagine riding on the slower spacecraft as the faster one passes by. In just 1 second, Voyager 1 would pull nearly a full mile ahead over a day. That adds up to tens of thousands of miles. Over years, it becomes millions of miles. Over the decades since they left the planets behind, Voyager 1 has pulled ahead by billions of miles. The gap continues to widen, a testament to the different paths they took through the solar system. The gravity assists at Jupiter and Saturn gave Voyager 1 more speed, accelerating it to its higher velocity. This speed is constant. There is no friction in space to slow them down, no air resistance, no drag. They will continue at this pace indefinitely, coasting through the void. The only forces acting on them now are the incredibly faint gravitational pulls of distant stars and the gentle push of solar radiation, neither of which significantly affects their trajectory. Solar radiation pressure is real, but tiny. Photons carry momentum, and when they strike an object, they exert a small force. For Voyager, this force is minuscule, only a fraction of an ounce. Even if every thruster failed and every system shut down, Voyager would continue moving forward at the same speed, unchanging for millions of years. In space, an object in motion stays in motion unless acted upon by an external force. Voyager embodies this principle perfectly. It is a monument to Newton's first law of motion, travelling through an environment where that law plays out in its purest form. There is no stopping, no slowing down, just endless motion through the void. The two spacecraft have now left the heliosphere. The terms solar system and heliosphere have very different meanings, and understanding this distinction helps us appreciate what Voyager has accomplished. The heliosphere is a bubble-like region of space dominated by the solar wind. The solar wind is made of charged particles streaming out from the sun, mostly protons and electrons. These particles race outward at speeds of about 300 miles per second. The sun constantly loses mass through this process, shedding millions of tons of material every second. The rate is about 1 million tons per second, which sounds like a lot, but over the Sun's lifetime of billions of years, it represents only a tiny fraction of the Sun's total mass. The Sun has lost perhaps 1/10% of its mass through the solar wind over its lifetime. Over the Sun's lifetime, it has lost a tiny fraction of its total mass through the solar wind. It forms a sphere around the Sun, but as the Sun moves through the galaxy, the solar wind gets compressed in front and stretched out behind, creating a bubble shape. Imagine a swimmer moving through water. The water pushes against them in front and flows smoothly behind. The heliosphere works in a similar way. In the direction of the Sun's motion through the galaxy, the heliosphere is compressed to a distance of maybe 10 billion miles. In the opposite direction, it stretches out into a long tail that might extend for hundreds of billions of miles. The exact shape is still being studied, and Voyager's data continues to refine our understanding. Some models suggest the tail might be hundreds of astronomical units long, extending far beyond the orbits of any planets. An astronomical unit is the distance from Earth to the Sun, about 93 million miles. The tail might extend 1,000 astronomical units or more, creating a vast, comet-like structure trailing behind the Sun as it orbits the galaxy. Voyager 1 crossed the boundary of the heliosphere in August of 2012. Scientists debated for months whether the crossing had actually occurred, carefully analysing the data. The spacecraft's instruments showed a sudden change in the environment. Solar particles dropped to nearly zero, while particles from interstellar space increased dramatically. But there was no corresponding change in the direction of the magnetic field, which confused scientists initially. They expected the magnetic field to change direction when Voyager left the heliosphere, but it did not. The magnetic field continued to point in the same direction, aligned with the Sun's magnetic field. This was puzzling. Eventually, they concluded that the magnetic field lines of the Sun extend beyond the heliopause, blending with the interstellar magnetic field in complex ways. The boundary is not as sharp as they had imagined. It is more of a transition zone than a clear dividing line. The heliopause is not a solid barrier, but a region where two plasmas meet and interact. Voyager 2 followed in November of 2018. They have exited the heliosphere. This graph shows actual data from Voyager during that crossing. The lower graph shows the number of solar particles dropping, while the upper graph shows a sudden rise in particles coming from interstellar space. The change was dramatic and unmistakable. Within just a few days, the character of the environment around the spacecraft completely transformed. So the heliosphere marks the limit of the Sun's influence through the solar wind. The boundary itself is not a sharp line, but rather a transition zone called the heliopause. In this region, the solar wind slows down and becomes turbulent as it collides with the interstellar medium, the thin gas that fills the space between stars. The interstellar medium is mostly hydrogen, with traces of helium and heavier elements. It is incredibly thin, with only 1 atom per cubic centimetre on average. By comparison, Earth's atmosphere at sea level contains about 10 to the 19th power atoms per cubic centimetre. The difference is staggering. Interstellar space is a near-perfect vacuum by any Earth standard, yet this thin gas exerts enough pressure to balance the solar wind, creating the heliopause. The pressure comes not from the density of the gas, which is negligible, but from its motion. The Sun is moving through the galaxy at about 50,000 miles per hour relative to the local interstellar medium. This motion creates a ram pressure, like the pressure you feel when you stick your hand out of a moving car window. The ram pressure of the interstellar medium balances the outward pressure of the solar wind, creating a boundary. The crossing into interstellar space was one of the most significant milestones in the history of space exploration. It marked the moment when a human-made object entered the realm between the stars, a place no spacecraft had ever been before. The achievement was celebrated by scientists and space enthusiasts around the world. It represented the culmination of decades of work, the fulfillment of a dream that began in the early days of the space age. When President Kennedy challenged America to go to the moon in 1961, it sparked an era of ambition and optimism. The speech, delivered to Congress, committed the nation to landing a man on the moon and returning him safely to Earth before the decade was out. It was a bold vision, one that seemed impossible at the time. Voyager is a product of that era, a mission that dared to reach beyond the familiar confines of the inner solar system. It inherited the can-do spirit of the Apollo program, the belief that nothing was impossible if you worked hard enough. But the heliosphere is not the edge of the solar system. This is an important distinction that often causes confusion. The solar system itself is much larger. For example, the Oort cloud lies far beyond the heliosphere. The Oort cloud is a theoretical region filled with icy bodies and rocks surrounding the Sun in a vast spherical shell. These objects are remnants from the formation of the solar system, frozen debris that never coalesced into planets. They orbit the Sun at enormous distances, so far out that their orbits take millions of years to complete. Some may take even longer, orbiting so slowly that a single circuit around the Sun might take tens of millions of years. These are objects that have barely moved since the solar system formed 4.5 billion years ago. They are time capsules, preserving material from the early solar system in deep freeze. According to some estimates, it will take Voyager another 300 years to enter the Oort cloud, and about 30,000 years to pass through it completely. Even then, it will still technically be within the gravitational influence of the Sun. The Oort cloud is thought to extend halfway to the nearest star, about 1 light-year from the Sun. Some estimates place the outer edge even farther, perhaps 2 light-years away. It is the source of long-period comets, icy visitors that occasionally fall inward and light up our skies. When a passing star disturbs the orbits of objects in the Oort cloud, some may be sent inward, heating up as they approach the Sun and developing the characteristic tails we associate with comets. These comets might take thousands of years to fall from the Oort cloud to the inner solar system, accelerating as they approach the Sun. They arrive from random directions, plunging through the planetary system at high speed. Some pass close to the Sun, developing spectacular tails that stretch millions of miles. Others remain at a distance, appearing as faint smudges in the night sky. The existence of the Oort cloud has never been directly confirmed, but its presence is strongly inferred from the orbits of long-period comets. These comets arrive from all directions, suggesting they come from a spherical shell surrounding the Sun. If comets came from a disk-like structure, like the Kuiper belt, they would arrive mostly from one direction. But long-period comets arrive from all directions equally, suggesting a spherical distribution. The Oort cloud may contain trillions of objects, a vast reservoir of primordial material. Some of these objects might be as large as dwarf planets, icy worlds that have never been seen by human eyes. The total mass of the Oort cloud is uncertain, but it might be equivalent to several Earth masses worth of material spread across an enormous volume. The density is so low that Voyager could fly through the Oort cloud for thousands of years without encountering anything. The Oort cloud represents the farthest extent of the Sun's gravitational domain, the true edge of the solar system. We can still send commands to the Voyagers and receive scientific data from them, but how is communication possible over such enormous distances? The answer lies in a combination of clever engineering, enormous antennas, and the fundamental physics of radio waves. The challenge is immense, and the fact that it works at all is a testament to decades of careful planning and design. Every aspect of the communication system was designed with extreme distances in mind, from the spacecraft's antenna to the receivers on Earth. The engineers who designed Voyager in the 1,970 seconds were planning for a mission that would operate at distances they could barely imagine. They built in margins of safety, redundancy, and efficiency that have allowed the mission to continue far longer than originally planned. Each Voyager has a dish antenna that is 12 feet across. This is the iconic feature most people picture when they think of the spacecraft. The antenna is made of lightweight aluminum mesh stretched across a frame, designed to be both strong and light. The mesh has holes in it, like a screen door, but the holes are small enough that radio waves reflect off it just as if it were solid metal. The size of the holes is determined by the wavelength of the radio waves being used. As long as the holes are smaller than the wavelength, the mesh acts like a solid surface. This design saves weight while maintaining performance. Every pound mattered during the design phase. The spacecraft had to fit within the payload capacity of the launch vehicle, and every component had to be as light as possible. Engineers spent countless hours optimizing every part of the design, shaving off ounces here and there. A solid dish would have been heavier and more expensive. The mesh design provided the same performance at a fraction of the weight. The weight savings allowed for more instruments, more fuel, or more power generation capacity. The antenna sends out a very narrow beam of radio waves, using just 22 watts of power, about the same as a household light bulb. The beam is focused so tightly that if it were aimed at Earth, it would cover an area smaller than the planet itself. This precise targeting is essential. Any wider, and the signal would be too weak to detect. The antenna must be pointed toward Earth with an accuracy of less than 1 degree. If it drifts off target by even 2 degrees, communication is lost entirely. The spacecraft uses a star tracker to maintain its orientation, locking onto bright stars like Canopus to ensure the antenna stays pointed in the right direction. Canopus is the second brightest star in the night sky, a giant star about 300 times more luminous than our Sun. Its brightness makes it an ideal reference point for navigation. The spacecraft also uses gyroscopes to sense any rotation, allowing it to maintain its orientation with extreme precision. The gyroscopes are mechanical devices that resist changes in orientation, providing a stable reference for the attitude control system. It takes about 22.5 hours for a signal to reach Earth. This means that when we send a command to Voyager, we have to wait nearly 45 hours for a response. By the time the signal travels there and back, almost 2 full days have passed. The delay makes operating the spacecraft a slow, methodical process. There are no real-time adjustments, no quick fixes. Every command must be planned carefully, and the team must wait patiently to see the result. If something goes wrong, the team cannot respond immediately. They must diagnose the problem based on old data, formulate a solution, send a command, and then wait another 2 days to see if it worked. This requires incredible patience and careful planning. The team must think ahead, anticipating problems before they occur. They run simulations, test commands on ground-based replicas of the spacecraft, and carefully verify every step before sending anything to Voyager. For comparison, it takes just over 1 second for light to travel from the Earth to the Moon, and about 20 minutes to reach Mars. This helps put Voyager's distance into perspective. The spacecraft is so far away that it exists in a different time frame from us. When we hear from it, we are hearing its past. The data arriving today shows what Voyager was experiencing yesterday. In a sense, we are always looking back in time when we communicate with Voyager. This is true for all astronomical observations. When we look at the Sun, we see it as it was 8 minutes ago. When we look at the nearest star, we see it as it was over 4 years ago. When we look at distant galaxies, we see them as they were billions of years ago. But it is particularly striking with Voyager because we built it and sent it on its way. We are literally communicating with the past, with a machine that left Earth decades ago and is now experiencing a reality we will not know about for nearly a day. Radio waves weaken with distance, following the inverse square law. This is a fundamental principle of physics that applies to all forms of electromagnetic radiation, including light, radio waves, and X-rays. This means that if you double the distance, the signal becomes 4 times weaker. If you triple the distance, it becomes 9 times weaker. The relationship is exponential. At 10 times the distance, the signal is 100 times weaker. At 100 times the distance, it is 10,000 times weaker. The signal spreads out in all directions, forming an expanding sphere. The energy is spread over a larger and larger area as the sphere grows. The surface area of a sphere increases with the square of the radius, hence the inverse square law. It is a geometric inevitability, a consequence of living in 3-dimensional space. By the time Voyager's 22-watt signal reaches Earth, it has faded to just a tiny fraction, less than 1 trillionth of a watt, and then another billionth of that. The signal arriving from Voyager is on the order of 10 to the minus 18th watts. To put this in perspective, a typical light bulb uses 60 watts. Voyager's signal, by the time it reaches Earth, is about 1 quintillion times weaker. The signal is so faint that it would take all the energy Voyager has transmitted in the past 4 decades just to power a single digital watch for a fraction of a second. To put it another way, the signal arriving from Voyager is about 1 billion times weaker than the power consumed by a cell phone battery. Detecting it requires the most sensitive radio receivers ever built. The signal is so weak that it is comparable to the faint whisper of radiation left over from the Big Bang, the cosmic microwave background that fills all of space. Radio astronomers who study distant galaxies and pulsars have developed techniques to detect such faint signals, and those same techniques are used to communicate with Voyager. The receivers use cryogenic cooling to reduce thermal noise, sophisticated signal processing to extract the signal from background noise, and long integration times to accumulate enough signal to be detectable. To detect such faint signals, NASA uses massive antennas. These antennas are 230 feet in diameter and are part of the Deep Space Network. Each dish weighs thousands of tons and stands as tall as a 20-story building. The dish itself is a parabolic surface precisely shaped to focus incoming radio waves onto a receiver at the focal point. The surface of each antenna is covered with aluminum panels precisely shaped to focus radio waves onto a receiver at the center. The panels must be aligned with extreme precision, accurate to within a fraction of a millimeter. Even a small distortion in the dish surface would degrade the signal. The dishes are so large that they must account for thermal expansion, wind loading, and even the gravitational sag of the structure. The temperature changes throughout the day cause the metal to expand and contract, slightly distorting the shape. The dishes have active surface control systems that adjust the panels to maintain the correct shape. The network is set up at 3 locations: California in the United States, Madrid in Spain, and Canberra in Australia. These sites were chosen because they are spaced roughly 120 degrees apart around the globe. This ensures that at least one antenna can always see the spacecraft at any given time, enabling round-the-clock communication. As Earth rotates, one station hands off to the next, creating a continuous link. The California site is located in the Mojave Desert, far from sources of radio interference. The site is called Goldstone, named after a nearby mining town from the California Gold Rush era. The desert location provides clear skies and minimal radio interference from cities, airports, and other sources. The Madrid site sits in the hills outside the city in a region called Robledo de Chavela. The site is about 40 miles west of Madrid, in a rural area with minimal radio interference. The Canberra site is located near the Australian capital, in a valley surrounded by low hills that help shield it from radio interference. Each site is carefully chosen for its low levels of radio interference, its clear skies, and its favourable geographic position. The sites are far from cities, airports, and other sources of electromagnetic noise. They are protected by radio quiet zones, areas where transmitters are restricted to prevent interference. Besides the massive 230-foot dishes, each location also has antennas of various other sizes. Some are 70 feet across, others are 34 feet. Together, they form a worldwide communication system designed to talk with spacecraft far beyond Jupiter. The dishes can also work together, combining their signals to boost sensitivity. This technique is called arraying. When multiple antennas are pointed at the same spacecraft, their signals are combined electronically, creating an even more sensitive receiver. The signals must be synchronized with incredible precision, accounting for the exact distance between the antennas and the arrival time of the radio waves. The timing must be accurate to within nanoseconds. A nanosecond is 1/billionth of a second. Light travels about 1 foot in a nanosecond. The synchronization is achieved using atomic clocks at each site, which are accurate to within billionths of a second. Thanks to these giant antennas, we can continue sending commands and receiving data from Voyager. The Deep Space Network also communicates with dozens of other spacecraft, including missions to Mars, the asteroid belt, and beyond. At any given time, the network might be tracking a rover on Mars, communicating with a spacecraft orbiting Jupiter, and listening to Voyager, all simultaneously. The network supports missions from NASA and from other space agencies around the world. It is a shared resource used by missions to all corners of the solar system. Scheduling time on these antennas is a complex process. Mission teams must request time in advance, balancing the needs of multiple spacecraft. Voyager is given priority during critical operations, but otherwise shares time with other missions. The network operates continuously, 24 hours a day, every day of the year. Engineers and technicians monitor the systems, making adjustments as needed to maintain contact with distant spacecraft. The Deep Space Network is one of the unsung heroes of space exploration, enabling missions that would otherwise be impossible. Without it, we would have lost contact with Voyager decades ago. It is a testament to long-term vision and investment in infrastructure. But transmitting signals and running instruments requires power. Voyager does not use solar panels because the sun is too faint at such great distances. Sunlight at Voyager's location is about 1,000 times weaker than it is near Earth. Solar panels would be useless. They would be too large and heavy to be practical. A solar array large enough to power Voyager at its current distance would need to be hundreds of feet across, far too big to fit on the spacecraft. At Earth's distance from the Sun, solar panels generate about 1,400 watts per square meter. At Voyager's current distance, they would generate less than 2 watts per square meter. To generate 200 watts, Voyager would need solar panels with an area of 100 square meters, about the size of a small house. Instead, it uses nuclear power. Radioisotope thermoelectric generators convert heat from decaying plutonium into electricity. The plutonium-238 decays naturally, producing heat. Plutonium-238 is different from the plutonium-239 used in nuclear weapons. Plutonium-238 is not suitable for weapons, but is ideal for power generation because it produces heat through radioactive decay. It emits alpha particles, which are stopped by a thin layer of material, making it relatively safe to handle with proper shielding. Special devices called thermocouples convert that heat into a steady electrical current. A thermocouple is a simple device made of two different metals joined together. When one end is heated and the other is cooled, it produces a small voltage. The principle was discovered in the early 19th century by Thomas Seebeck, a German physicist. Voyager uses hundreds of thermocouples to convert the heat from the plutonium into usable electricity. The efficiency is low, only about 6%, but the system is reliable and requires no moving parts. Most of the heat is wasted, but there is no shortage of heat. The plutonium produces heat continuously, whether it is used or not. The generators are remarkably reliable, with no moving parts to break down. They sit at the end of a boom extending from the spacecraft, positioned away from the sensitive instruments to minimize radiation exposure. Each generator is about the size of a small trash can, containing several pounds of plutonium oxide pellets. The pellets are sealed in multiple layers of protective material to prevent any release of radiation. The design has been extensively tested and has never failed in any mission. The same type of generator has powered many spacecraft, from Pioneer to New Horizons. At launch, each Voyager produced over 400 watts of power. Now, after decades of flight, power output has dropped below 200 watts. This decline is inevitable. As the plutonium decays, it produces less heat. The rate of decay is predictable, following a curve that engineers calculated long ago. Plutonium-238 has a half-life of about 88 years, meaning that in 88 years, half of it will have decayed. By the time Voyager launched, engineers knew exactly how much power it would have at every point in its mission. They planned accordingly, designing systems that could be shut down as power declined. They knew that eventually power would become scarce, and difficult choices would have to be made about which systems to keep running. The power decline is about 4 watts per year, a slow but steady decrease. To conserve energy, non-essential systems have been shut down gradually. The spacecraft no longer uses heaters to keep certain instruments warm. Some instruments can tolerate the cold, operating at temperatures far below what they were designed for. The engineers who built these instruments never imagined they would be operating at temperatures near absolute zero, but they have proven remarkably resilient. Some backup systems have been turned off. Every watt is precious now. The team carefully monitors power levels and plans years in advance which systems to shut down next. Each decision involves trade-offs, balancing the scientific value of instruments against the need to keep critical systems running. The attitude control system must keep working, or the antenna will drift off target. The radio transmitter must keep working, or communication will be lost. Everything else is negotiable. The decisions are made by a committee of engineers and scientists, weighing the pros and cons of each option. This is a photograph of Earth taken by Voyager, our home seen from nearly 4 billion miles away. The image shows Earth as a tiny pale blue dot, barely a single pixel, suspended in a beam of scattered sunlight. It appears as a speck, almost lost in the vastness of space. If you did not know where to look, you might miss it entirely. The photo was taken on February 14th, 1990, at the request of astronomer Carl Sagan, who had been involved with the Voyager mission from the beginning. Sagan wanted a family portrait of the solar system, a final look back at the planets before Voyager's camera was shut down. The idea was controversial. Some engineers worried that pointing the camera toward the sun might damage the sensitive optics. The camera was designed to photograph planets, not to look near the sun. But Sagan persisted, and the team carefully planned the sequence to minimize risk. They calculated the exact angles, ensuring the sun would not shine directly into the camera. The image became known as the pale blue dot. It was the last picture Voyager 1 ever took. After that, its camera was permanently turned off to save power. The cameras were designed for close encounters with planets, not for deep space observations. Once the planetary tour was over, they were no longer needed. Shutting them down freed up power for more essential tasks. The image became one of the most famous photographs in history, reminding us of our place in the universe. Sagan later wrote about the photograph, reflecting on how it shows everyone we have ever known, every civilization, every triumph and tragedy, all contained on that tiny dot suspended in a sunbeam. He spoke of how it underscores our responsibility to be kind to one another and to preserve our world, the only home we have ever known. The photo has been called the most important image ever taken, not for its technical quality, but for what it represents. It shows our world as it truly is, a fragile oasis in an immense cosmic arena. Sagan's reflections on the image have been read by millions, inspiring a sense of perspective and humility. Voyager 1 carries 10 scientific instruments. These include devices to measure magnetic fields, charged particles, plasma waves, and cosmic rays. There are magnetometers to detect magnetic fields, plasma detectors to measure the solar wind, cosmic ray detectors to study high-energy particles from outside the solar system, and instruments to measure radio waves and plasma oscillations. Some instruments measure the strength and direction of magnetic fields. Others count particles, determining their energy and composition. Some detect radio emissions from the sun and from interstellar space. Each instrument was state-of-the-art in 1977, designed by teams of scientists and engineers who poured years of effort into their development. Each instrument has its own story, its own team of dedicated people who worked to make it possible. Only those measuring magnetic fields and charged particles are still in use. With just these, it continues to study the interstellar environment beyond the heliosphere. The data it sends back helps scientists understand the boundary between our solar neighborhood and the space between the stars. For instance, the instruments have detected variations in the density of interstellar gas and have measured the strength of the interstellar magnetic field. The interstellar magnetic field is surprisingly strong, about 10 times stronger than scientists expected. This field may help shield the solar system from some cosmic rays, high-energy particles that originate from supernova explosions and other violent events in the galaxy. These cosmic rays can damage spacecraft electronics and pose a hazard to future interstellar missions. Understanding the interstellar environment is essential for planning future missions that might travel even farther than Voyager. The data from Voyager is unique, irreplaceable. No other spacecraft has made these measurements, and none will for the foreseeable future. However, power output from the nuclear battery continues to decline. NASA is carefully planning when to shut down each remaining instrument. Each decision is difficult, weighing scientific value against the reality of diminishing power. The science team meets regularly to discuss priorities, knowing that each instrument they turn off represents the end of decades of discovery. Some instruments provide unique data that cannot be obtained any other way. Voyager is the only spacecraft in interstellar space, providing the only direct measurements of that environment. Others have been operating for so long that they provide a continuous record spanning decades, invaluable for understanding long-term trends. The magnetic field instrument has been operating continuously for over 40 years, providing an unprecedented dataset. Even after all instruments are turned off, Voyager will still be able to transmit basic information, like its location. The spacecraft will continue to send a carrier signal, a simple tone that lets engineers on Earth know it is still functioning, but eventually, even that will stop. Over the decades, the Voyagers have encountered some technical issues. These challenges have tested the ingenuity of the engineering team back on Earth. Each problem requires careful analysis, creative thinking, and sometimes a bit of luck. The team has become expert at diagnosing and fixing problems on a spacecraft billions of miles away, using decades-old technology. They have developed a deep understanding of how the spacecraft works, how its systems interact, and how to work around limitations. In 2023, Voyager 2 experienced a problem when its antenna drifted off by just 2 degrees. That may not sound like much, but at billions of miles away, even a tiny angle shift becomes critical. It was enough to cut off communication entirely. The narrow beam of radio waves missed Earth completely. For several anxious days, the team lost contact with the spacecraft. They could not send commands, could not receive data. They could only wait and hope. The team worried that they might have lost Voyager 2 forever, that it might drift silently through space with no way to re-establish contact. The problem occurred after a routine command sequence, when the spacecraft was told to update its pointing. A coding error caused it to point in the wrong direction. NASA had anticipated this scenario. Voyager was pre-programmed to automatically correct its orientation a few times each year. The spacecraft uses onboard sensors to lock onto certain bright stars, using them as reference points to maintain alignment. Canopus, a bright star in the southern sky, serves as one of these reference points. The spacecraft measures the position of the star and adjusts its orientation accordingly. The star tracker is a simple device, essentially a telescope with a photomultiplier tube that measures the brightness and position of stars. Sure enough, it reoriented itself, and communication was restored. The team on Earth breathed a collective sigh of relief. It was a reminder of how delicate the connection is, and how much foresight the original engineers put into the spacecraft's design. They had planned for this exact situation decades in advance, programming the spacecraft to fix itself if it lost contact with Earth. The autonomous correction worked perfectly, a testament to careful engineering and planning. The team celebrated, grateful for the foresight of the original designers. Voyager 1 also ran into trouble when a software issue caused it to send data through a deactivated computer. The spacecraft has 3 onboard computers. One handles commands and flight control, another processes scientific data, a third manages attitude control and pointing. Each computer has a backup, providing redundancy in case of failure. The computers are incredibly simple by modern standards, with less memory than a basic digital watch. The problem arose when one of these computers tried to route data through a system that had been shut down to save power. The result was garbled data, incomprehensible strings of numbers that made no sense. The data appeared to be random noise, with no discernible pattern. NASA spent months diagnosing the problem, and eventually sent a new command, directing it to use a working computer. This resolved the issue, but the process was slow and delicate. Every command had to be sent, then the team had to wait almost 2 days to see if it worked. Engineers had to dig through documentation from the 1,970 seconds, finding old code written in outdated programming languages, trying to understand exactly how the spacecraft would respond. The documentation was stored in filing cabinets, on paper printouts that had yellowed with age. Some of the code was written on punch cards, long since archived. The engineers pored over the documents, studying flowcharts and diagrams drawn by hand. It was like trying to fix a 40-year-old car with only the original manual to guide them. The code was written in assembly language, low-level instructions that directly control the computer's hardware. Few people still understand these old programming languages, and the engineers who originally wrote the code have mostly retired. Some were brought back as consultants, sharing their knowledge with younger engineers who had never worked with such old systems. The younger engineers marveled at the elegance and efficiency of the old code, written in an era when every byte of memory had to be carefully managed. There was no wasted space, no unnecessary instructions. Every line of code served a purpose. NASA is also planning for future problems, such as thruster valve blockages. The Voyagers use small thrusters to maintain their orientation for communication. These thrusters fire in short bursts, unlike main engines. They use hydrazine fuel, which decomposes into hot gas when passed over a catalyst bed. The hot gas shoots out through tiny nozzles, providing just enough force to nudge the spacecraft back into alignment. Each thruster firing lasts only a fraction of a second, producing only a few ounces of thrust, but over decades, these tiny adjustments add up. The spacecraft has fired its thrusters millions of times over the course of its mission. Each firing uses a tiny amount of fuel, but the fuel supply is finite. Over decades, propellant residue can build up and clog the system. The hydrazine breaks down into ammonia and nitrogen, but not all of it burns cleanly. Some residue accumulates in the fuel lines and valves, gradually restricting flow. The problem is similar to how mineral deposits can clog old plumbing in a house. The deposits build up slowly, unnoticed, until suddenly the flow is reduced. NASA updated the software to extend the duration of each thruster firing. This reduces the number of times the thrusters need to fire and is expected to extend their life by about 5 more years. By firing the thrusters for slightly longer periods, the spacecraft needs fewer corrections overall. Each longer firing uses the same amount of fuel as several short firings, but reduces wear on the valves. The valves are mechanical devices, and every time they open and close, they experience a tiny amount of wear. Reducing the number of firings extends their lifespan. Engineers also switched to backup thrusters that had not been used in decades, testing them carefully to make sure they still worked. The backup thrusters were designed for planetary encounters, meant to help adjust the spacecraft's trajectory during close flybys. They had been dormant for 37 years, sitting unused as the primary thrusters did all the work. When engineers fired them up, they worked perfectly, a testament to the robust design and careful engineering. The valves opened, the fuel flowed, and the thrusters fired exactly as designed. It was a moment of celebration for the team, proof that decades-old hardware could still function flawlessly. The success demonstrated that well-designed systems can last far longer than their designers ever imagined. The thrusters had been tested on the ground before launch, then sat idle for decades, and still worked when called upon. Despite these challenges, both Voyagers continue their journey and maintain communication with Earth. However, as they get farther away, signal strength continues to decline. NASA expects that by 2036, communication will likely end. That means we have at most about 10 years left to communicate with Voyager 1. The end will come not from a catastrophic failure, but from a gradual decline. Power will drop below the threshold needed to run the transmitter, or the signal will become so faint that even the deep space network cannot detect it. The signal is already at the edge of detectability, requiring the most sensitive receivers and long integration times. As Voyager moves farther away, the signal will become weaker and weaker until it finally disappears into the noise. After that, the spacecraft will continue traveling in silence. It will still be there, moving through the galaxy, but we will no longer hear from it. The connection will be lost, not because Voyager stops working, but because the signal becomes too faint to detect, or the power runs out entirely. The final message from Voyager will be a quiet end to one of humanity's greatest achievements. A gentle farewell from the most distant emissary we have ever sent. Engineers are already planning for that day, deciding how to mark the end of communication, how to preserve the mission's legacy. Some suggest a final command sequence, a ceremonial goodbye, perhaps instructing Voyager to turn off its instruments one by one. Others think it should be allowed to fade naturally, without fanfare, allowing the mission to end as it has proceeded, with quiet dignity. Either way, it will be a bittersweet moment, the end of an era. The last signal will be weak, fading gradually until it disappears into the cosmic background noise, and then silence. The team will gather, knowing they have heard the last transmission from Voyager. There will be sadness, but also pride in what has been accomplished. Voyager 1 and Voyager 2 were launched in 1977. Their mission was originally planned to last only 5 years. However, they have been operating for more than 40 years, far exceeding the initial plan. They have left the heliosphere and continue to send data back to Earth. The engineers who built them could not have imagined how long they would last. When the spacecraft were designed, 5 years seemed ambitious. The harsh environment of space, the intense radiation near Jupiter, the extreme temperatures, all posed threats to the spacecraft's survival. No one expected them to still be functioning in the 21st century. Some engineers privately gave them a 50-50 chance of making it to Saturn. The success has exceeded everyone's expectations. The spacecraft were designed with redundancy and simplicity in mind, using proven technology and robust materials. That conservative approach paid off. Many of the engineers who worked on Voyager have retired, but some remain involved, passing their knowledge to a new generation. The mission has become a bridge between generations, connecting the optimism of the 1,970 seconds space program with the sophisticated missions of today. Young engineers who were not even born when Voyager launched now work to keep the spacecraft operating, learning from the original designers, preserving their knowledge and expertise. Some of the original engineers serve as mentors, sharing stories of the early days when everything was new and uncertain. They speak of the challenges they faced, the problems they solved, the triumphs and the setbacks. They speak with pride of what they accomplished, of building something that has lasted longer than they ever dreamed. The memory capacity of the Voyagers is about 1/13 millionth of that of a modern smartphone. Their communication speed is about 1/138,000th of today's standard. The computers on board use magnetic tape for data storage, similar to cassette tapes. The tape stores data magnetically, just like old audio cassettes or VHS tapes. The tape is 8 tracks wide, with data recorded along the length. They have less computing power than a basic calculator. The onboard memory can store only about 67,000 words, roughly the length of a short novel. The computer's processor operates at a speed of about 250 kHz, millions of times slower than a modern smartphone. A modern smartphone processor operates at speeds of several gigahertz, billions of cycles per second. Although the technology was state-of-the-art at the time, it has now become outdated. In 1977, this was cutting-edge technology. Personal computers were rare. The Apple II had just been released, with 16 kilobytes of memory and costing over $1,000. The internet did not exist. Cell phones were a decade away. Today, it seems almost primitive, a modern car has more computing power than Voyager. Despite carrying old equipment, these probes have reached the farthest points from Earth and represent the forefront of space exploration. They are a reminder that sometimes simplicity and reliability matter more than raw computational power. Modern spacecraft carry far more sophisticated computers, with millions of times more memory and processing power, but none have travelled as far or lasted as long as Voyager. The lesson is clear. Robust design and conservative engineering can outlast flashy technology. Sometimes, the simplest solution is the best solution. The engineers who designed Voyager understood this. They used tried and tested technology, built-in redundancy, and designed for the long term. Each Voyager also carries a golden record, a 12-inch gold-plated copper disc. The record contains sounds and images selected to portray the diversity of life and culture on Earth. It includes greetings in 55 languages, music from different cultures, and natural sounds like wind, rain, and birdsong. The greetings range from ancient languages like Sumerian to modern languages like Mandarin and English. The Sumerian greeting is a reminder of one of the earliest civilizations, now long gone. The cuneiform script of Sumeria has not been used for thousands of years, yet it travels aboard Voyager, a link to humanity's ancient past. The music includes Bach, Beethoven, Chuck Berry, and traditional songs from around the world. There are classical works, folk songs, and rock and roll, representing the full spectrum of human musical expression. Bach's Brandenburg Concerto represents the heights of Western classical music. Chuck Berry's Johnny B. Good represents rock and roll, the energetic popular music of the 20th century. There are songs from Java, Peru, Japan, and Azerbaijan, showing the diversity of human cultures. There are also 116 images encoded in analog form. The images show scenes of daily life, scientific diagrams, pictures of Earth's landscapes, and photographs of people from around the world. There are images of DNA structures, mathematical equations, a sunset, a mother nursing her baby, a traffic jam, and much more. The images include pictures of animals, buildings, scientific instruments, and human activities. There is an image of a fetus showing the beginning of human life. There are images of people eating, working, and playing. The selection was carefully curated by a committee led by Carl Sagan, trying to capture the essence of human civilization in a handful of images. Each image was debated and discussed. What should be included? What represents humanity? How do you capture the richness of human culture in 100 images? Some images were rejected as too controversial or too culturally specific. Others were chosen for their universal appeal. The record is a message to any intelligent life that might encounter the spacecraft in the distant future. Instructions for playing it are etched on the cover, along with symbols explaining where Earth is located relative to 14 pulsars, rotating stars that emit regular pulses of radio waves. The pulsars act as cosmic lighthouses, their precise timing serving as a clock and a map. Each pulsar has a unique period, like a fingerprint. By measuring these periods, an alien civilization could triangulate Earth's location in the galaxy. The diagram shows the position of the Sun relative to the center of the galaxy and to nearby pulsars. The lines radiating from the center represent the direction and distance to each pulsar, with binary notation indicating their periods. A small sample of uranium-238 is included as a radioactive clock, allowing any finder to determine how long ago the spacecraft was launched. By measuring how much of the uranium has decayed, an alien civilization could calculate when Voyager left Earth. Uranium-238 has a half-life of 4.5 billion years, about the age of the Earth. By measuring the ratio of uranium to lead, the decay product, the age of the record, can be determined with precision. The inclusion of the uranium sample was a stroke of genius, providing a universal clock that any technological civilization could understand. It is a time capsule, a greeting from humanity to the cosmos. The chances of it being found are incredibly small, almost infinitesimal, but it represents hope, curiosity, and our desire to reach beyond ourselves. The galaxy contains hundreds of billions of stars. The chance of Voyager encountering one is vanishingly small. The space between stars is vast, and Voyager is a tiny needle in an enormous haystack. Even if the record is never found, it serves a purpose. It reminds us of our place in the universe, of our achievements and our potential. It is a statement of who we are, frozen in gold, traveling through the void. It says, we were here, we existed, we created music and art and science, and we sent this message hoping someone, someday, might hear it. It is an act of faith, a message in a bottle cast into the cosmic ocean. By transmitting very weak radio signals, they stay connected to Earth and will continue to travel through unexplored space in the future. Long after communication ends, Voyager will drift onward. In about 40,000 years, Voyager 1 will pass within about 1.5 light years of a star called Gliese 445. It will be the closest approach to another star for many thousands of years. Even then, it will still be incredibly far away. 1.5 light years is about 9 trillion miles. To put this in perspective, if Voyager were the size of a grain of sand, Gliese 445 would still be miles away. Gliese 445 is a small red dwarf star, much dimmer than the Sun. Any planets it might have would be cold and dark, illuminated by a feeble reddish glow. The encounter will be brief, lasting only a few thousand years as Voyager passes through the outer reaches of the star system. But it will be out there, carrying its golden record, a silent ambassador from a distant world. Voyager 2 will pass near a star called Ross 248 inches, about 40,000 years, and then near Sirius, the brightest star in our night sky, in about 300,000 years. Sirius is a binary star system, consisting of a bright white star and a dim white dwarf companion. The white dwarf is the remnant of a star that has exhausted its fuel and collapsed. Neither spacecraft will come anywhere close enough to be captured by these stars. They will simply drift past, silent and alone. The encounters will be brief, lasting only a few thousand years as Voyager crosses through the outer regions of those star systems. From the perspective of those star systems, Voyager will be just another small asteroid passing through the outer darkness, unnoticed and unremarked. The spacecraft will continue traveling for millions, perhaps billions of years. They may outlast human civilization itself. Long after Earth has changed beyond recognition, Voyager will still be out there, moving through the galaxy. In a sense, they are immortal. They will drift through the Milky Way, silent and alone, until perhaps one day they encounter another intelligence, or perhaps until the stars themselves grow cold. In billions of years, the Sun will expand into a red giant, eventually shedding its outer layers and becoming a white dwarf. Earth will be consumed, vaporized in the Sun's outer atmosphere. The oceans will boil away, the rocks will melt, and eventually Earth will be engulfed. But Voyager will still be out there, untouched, unchanged, traveling through the void. The universe itself might change around Voyager. Stars will be born and die. The Milky Way will collide with the Andromeda Galaxy in about 4 billion years, creating a new merged galaxy. The collision will be spectacular, with stars passing by each other some flung into intergalactic space. Voyager will witness this merger, though there is no one aboard to see it. Despite the name, galaxy collisions rarely involve actual collisions between stars. The distances between stars are so vast that they mostly pass by each other. But the gravitational interactions will reshape both galaxies, triggering bursts of star formation and sending some stars into new orbits. Galaxies will collide and merge. But Voyager will continue, a tiny artifact from a long-vanished civilization, still carrying its message. In some distant future, if the record is ever found, it might be the only evidence that humans ever existed. Our cities will crumble, our monuments will erode, even our bones will decay. All traces of our civilization will vanish, worn away by time, but Voyager will endure, preserved by the vacuum of space. They are monuments to human curiosity, to our drive to explore and understand the universe, and to the remarkable ingenuity of the people who built them and sent them on their way. They represent the best of what humanity can achieve when we work together toward a common goal. The Voyager missions involve thousands of people, from engineers and scientists to technicians and administrators. Each person played a role, contributing their expertise to make the mission possible. They came from different backgrounds, different countries, united by a common purpose. Some designed instruments, others wrote software, still others built the hardware. Some tested components, others analyzed data. The mission was a collaborative effort, a testament to what people can accomplish when they work together. They are a message to the future, a statement that we were here, that we looked up at the stars and wondered, and that we had the courage and the vision to reach out and touch them. In an age when the world often seems divided, Voyager reminds us of what we can accomplish when we unite behind a common purpose. It is a legacy that will endure long after we are gone, a testament to human achievement that will travel through the cosmos for eternity. Voyager carries our hopes, our dreams, our music, our voices. It carries the best of what it means to be human. It carries us into the future, into the unknown, carrying a message that says we were here, we wondered, we explored, and we reached for the stars.